At Oxford University, there is a researcher who has spent his entire career thinking about how humanity survives the next 1,000 years. His name is Nick Bostrom, and in 2008, he admitted something that sounded almost unscientific. He said he hopes our Mars probes find nothing. No microbes, no fossils, no trace of anything that ever lived, just dead rocks. Why would the man whose job is humanity's future hope that the most famous scientific search of our era fails completely? That is what we're going to unpack tonight. Stay with me, because there are 33 sealed tubes sitting on Mars right now, scheduled to be brought back to Earth around 2031, and one of them may be holding his worst fear. If you are new here, hit like and subscribe. Pour yourself something warm, get comfortable, because tonight I am walking you through why a handful of scientists are quietly praying the universe gives us the one result nobody expected to hope for, and exactly what Nick Bostrom was really afraid of. Now, let's ease into this. Part 1. The sentence that breaks the narrative. I hope that our Mars probes will discover nothing. Dead rocks and lifeless sands would lift my spirit. Read that again, slowly. Let it sit there for a moment, because something about it should feel wrong to you, and that wrongness is the entire reason we're here tonight. The sentence was written in 2008 by a philosopher named Nick Bostrom, and if you've never heard of him, that's okay, but you should know who he is before we go any further, because without that context, the sentence just sounds like the grumbling of someone who doesn't like space exploration, and that is absolutely not what this is. Nick Bostrom is the founder of the Future of Humanity Institute at the University of Oxford. His entire career, the thing he gets out of bed for every morning, is trying to figure out what happens next for our species. Not next year, not next decade, next century, next millennium, next 100,000 years. He's the guy who spends his days thinking about artificial intelligence, genetic engineering, asteroid impacts, pandemics, and the various ways a civilization like ours either survives the next few centuries or quietly vanishes from the cosmic record. He is, by any reasonable measure, one of the most serious thinkers about humanity's long-term future walking the planet right now. So let that sink in for a second. The man whose literal job is hope for our future, the man who studies what it takes for humanity to flourish across the coming millennia, wrote down in black and white that he hopes our Mars probes find nothing, that he would feel his spirit lifted if we discovered that Mars was utterly, completely, tragically dead. Now, you have to understand how strange this is in context. Ask almost any other scientist alive what they would most want to discover, and they will tell you some version of the same thing. Life beyond Earth. One single microbe on another world. One ambiguous fossil in a core sample. One biosignature that can't be explained by chemistry alone. The search for extraterrestrial life is arguably the single most celebrated scientific quest of our era. It is the reason billions of dollars get poured into rovers, orbiters, telescopes, and sample return missions. It is the question that shows up on the first day of every astrobiology class. Are we alone? And here is one of the most respected thinkers on the subject, telling us that he is quietly praying the answer is yes, that the cosmos around us is empty, that Mars is a graveyard. Why? That's the question I want you to hold in your head for the next few hours of your life, because we are going to walk through this slowly and carefully, and by the end, I think you will understand not only what Bostrom meant, but why a small, growing group of astrobiologists, physicists, and philosophers are quietly hoping the same thing. And why that hope, strange as it sounds, may be the most rational position any of them could possibly take. Because while we sit here tonight, 93 million miles away, in a dusty crater on a cold, rust-coloured world, 33 sealed metal tubes are sitting on the surface of Mars. They're about the size of a large cigar, made of titanium, hermetically sealed against contamination, and arranged in small deposits along the floor of Jezero Crater. They were drilled and filled one by the Perseverance rover over the past several years, They contain rock cores, regolith, and atmospheric samples pulled from locations that, billions of years ago, may have been the bottom of a lake. Those tubes are real. They exist right now. They are not a concept. They are not a plan. They are physical objects sitting on the surface of another planet, waiting for someone to come pick them up and bring them home. And inside one of them, possibly, almost certainly maybe, is the single most important piece of scientific evidence in the history of our species. We just don't know which one. Here is the thing that breaks the normal narrative. For most of us, if I told you that there might be life in one of those tubes, your immediate reaction would be excitement, wonder, the beautiful feeling that the universe is not a lonely place, that we have cosmic company, that somewhere in the long story of matter and energy, we have cousins. That is the story we have been told our entire lives, from every science fiction movie, every planetarium show, every National Geographic documentary. Finding life out there is supposed to be the good ending. But what if it isn't? What if discovering life on Mars, specifically life that arose independently from our own, would be the worst news our species has ever received? Not the best, the worst. What if that discovery, made in a laboratory somewhere in the early 2030s, would mathematically imply that humanity's future is shorter than we think? Much shorter. Not because of anything Mars did, not because of some contamination or infection or invasion fantasy, but because of something much colder than that, something written into the statistics of the universe itself. That is what Bostrom was talking about, and it is not a fringe view, it is not paranoia, it is a logical consequence of a framework that has been quietly haunting a certain corner of the scientific community for almost 30 years now, and which almost no one outside that community has ever properly heard of. The answer to why he wants Mars to be dead is not about Mars at all. It is about us. It is about a door we may be walking through without knowing it. And the tubes sitting in Jezero Crater right now are the key that may be about to unlock it. In roughly the next 10 years, we're going to find out which side of that door we're on. And the people who understand what that means are quietly starting to sweat. Part 2. The tube on the surface of another world. Let me tell you about one tube in particular. Imagine, if you can, a small piece of hardware roughly 6 inches long, shaped like a narrow cylinder, machined out of surgical-grade titanium. Inside it is a few grams of Martian rock, drilled from a specific outcrop by the Perseverance rover, using a rotary percussive drill mounted on its robotic arm. The moment that rock was drilled, the core was slid into the tube was sealed, and a small gasket inside it closed off the contents from the Martian atmosphere. The rover then placed that tube gently on the ground, in a carefully chosen location where it will sit, undisturbed, until something or someone comes back for it. Those placements are not random. Perseverance has been dropping these tubes in specific caches, each one mapped, photographed, and catalogued. Every core has a name. Every core has coordinates. Every core has a geologic story attached to it. Some came from clay-rich mudstones. Some came from sulfate-bearing rocks. Some came from igneous outcrops that might tell us about the age of the crater floor. And a few, a precious few, came from rocks that bear features that nobody has been able to fully explain using non-biological chemistry alone. I want you to hold that image in your mind. A titanium cigar, sitting on red dust, under a thin pink sky, next to rover tracks, near a crater wall that used to be a shoreline. And inside it, sealed away from everything, are molecules that may have been sitting in that rock for 3 billion years, waiting. Now here is where it connects to something Perseverance's older cousin found first. Before Perseverance ever landed, a rover named Curiosity was driving around in a different crater, Jezero Crater, on the other side of the planet. Curiosity carried a little oven on board called SAM, short for Sample Analysis at Mars. You feed it a pinch of crushed rock, it heats that pinch up to very high temperatures, and a mass spectrometer reads the gases that come off. It is, in effect, a tiny chemistry lab with wheels, driving around another world. In a place called Yellowknife Bay, Curiosity drilled into a rock formation we now call the Cumberland mudstone. That mudstone had formed at the bottom of an ancient lake billions of years ago, when Mars had liquid water and possibly a thicker atmosphere. And when Curiosity cooked a sample of Cumberland in SAM's oven, something strange came off. Long-chain hydrocarbons, specifically molecules called decane, undecane, and dodecane, chains of 10, 11, and 12 carbon atoms, linked together in the kind of orderly arrangement that, here on Earth, we almost exclusively associate with life. These findings were formally published in the Proceedings of the National Academy of Sciences in 2025, and they represent the longest chain organic molecules ever detected on Mars. That matters. It matters a lot. Because on Earth, chains like these are the kind of thing you find in the breakdown products of fatty acids. Fatty acids are the building blocks of cell membranes. Cell membranes are what separate a living thing from its environment. Every single cell in your body is wrapped in one. When biology dies and decomposes over long stretches of time, the membranes fall apart in characteristic ways, and one of the most common residues left behind is a suite of long-chain alkanes, numbered just like these. Now, I want to be scrupulously fair here, because the scientists who made this discovery they did not announce that they had found life. They announced that they had found molecules whose biological origin is a reasonable hypothesis, but not a confirmed one. There are ways to make long-chain hydrocarbons without life. Deep inside the Earth, in hydrothermal systems, there is a process called Fischer-Tropsch synthesis, where carbon monoxide and hydrogen react in the presence of metal catalysts at high pressure and temperature, and they produce hydrocarbon chains that can look, chemically, similar to what Curiosity detected. If Mars had that kind of chemistry happening in its crust billions of years ago, you might get decane and undecane and dodecane without a single living cell ever being involved. So we can't be certain, not yet. But here is why this matters for the story we're telling. The molecules Curiosity found are not in a tube on their way to Earth. Curiosity does not have the ability to seal and cache samples. Those findings are stuck on Mars, analysed only by the limited instruments on the rover itself. Perseverance, on the other hand, is specifically designed to drill, seal, and cache samples from rocks that look just as promising. And some of the 33 tubes currently sitting on the Martian surface were drilled precisely because the rocks they came from have features that echo the ones Curiosity saw, which means this. Right now, as you're hearing my voice, there are probably tubes on Mars containing molecules that, if analysed with the full suite of instruments available in a modern Earth laboratory, could answer the question that has haunted us for centuries. Did Mars independently from Earth host life? And remember, this is the question that Nick Bostrom, the man who runs the Future of Humanity Institute, hopes will be answered in the negative. Because if those tubes come back, and the molecules inside them turn out to be the fingerprints of a second independent biology, then the statistical universe we thought we lived in is not the universe we actually live in. And what replaces it is a much darker picture, a picture in which the silence of the cosmos is not an accident, it is a warning. And the fact that life may be common makes the warning louder, not quieter. Those molecules in those tubes may soon decide whether the silence ahead of us is an empty hallway or a closed door, and something is about to come pick them up. Part 3. The Race We Didn't Expect. For years, the plan was an American-led mission called Mars Sample Return, a complicated relay of spacecraft that would land on Mars, collect the tubes Perseverance had dropped, launch them into Martian orbit, rendezvous with a return vehicle, and bring them home. The cost estimates kept climbing. $11 billion. Then higher. The mission architecture kept shifting. NASA was forced to go back to the drawing board. In the meantime, while the United States debated budgets and architectures, another space agency quietly moved forward. China's Tianwen-3 mission is now scheduled to launch in its primary window in 2028, with samples expected back on Earth around 2031. It is not a complex multi-mission relay. It is simpler. It will land, drill, collect, and return. If the current schedule holds, Tianwen-3 will bring back more than 500 grams of Martian material from a site chosen for scientific interest. That is a significant mass of rock, regolith and dust from another world, delivered to a terrestrial laboratory within the decade. And here is the thing you need to understand. Whether it is Tianwen-3 or a revised American effort or both, the samples are coming. The question of whether Mars hosted life is no longer theoretical. It is scheduled. There is a date on a calendar, somewhere in the early 2030s, when that question gets an answer. And when it does, the answer will fall into one of two categories. And depending on which one it is, Nick Bostrom's sentence from 2008 is either an overreaction or a prophecy. That is why Tianwen-3 matters so much more than its engineering. It is the mission that could reveal which side of the Great Filter we are on. Because the Great Filter, and we're about to get deep into this, says that somewhere in the long pipeline between lifeless matter and galactic civilization, there is a step that almost nothing gets past. And Mars, of all places, is about to tell us whether that step is behind us or ahead. Part 4. The evidence stack nobody talks about together. Here is what I want you to do. Forget for a moment the question of whether any single piece of evidence from Mars proves that life was ever there, because no single piece does. Not the hydrocarbons in Cumberland mudstone, not the ancient lakes, not the delta formations, not the clays, not any of it, alone. Now stack them all on top of each other. That is where it gets uncomfortable. Start with water. We now know, with considerable confidence, that Mars had an ocean roughly 3.37 billion years ago, covering a significant portion of its northern hemisphere. We know this from shorelines preserved in the topography, from sediment patterns, from isotopic signatures in the atmosphere that track how much water Mars has lost to space over the eons, and from minerals that only form in the presence of liquid water. That ocean did not just sit there briefly. It lasted long enough to leave unmistakable geological fingerprints. Jezero Crater, the place where Perseverance is currently working, is itself a piece of evidence. It is the remains of an ancient lake, fed by a river that deposited an unmistakable delta at the crater's edge. Deltas form when a river carrying sediment slows down as it enters a larger body of water, dropping its load in a characteristic fan shape. We see that fan at Jezero. We can walk the rover up its layers. We can read the sedimentary record like a page of text. And what the page says is that Jezero was wet, calm and stable for a long time. Not a flash flood, not a brief thaw. A lake, with a river feeding it, for a geologically meaningful stretch. Then add the kaolinite. Kaolinite is a type of clay mineral that is very picky about how it forms. You cannot make kaolinite quickly. You cannot make it from a brief splash of water. It requires sustained rainfall, warm temperatures, and long periods of chemical weathering. It forms in soils that have been exposed to liquid water for thousands or millions of years. And we have detected kaolinite on Mars in multiple locations, which means at some point parts of that planet were not just wet, they were warm, rainy and wet for a very long time. Then add the leopard spot patterns. Perseverance has found rocks at Jezero with peculiar chemical signatures, small spots enriched in iron and phosphorus, arranged in patterns that, on Earth, are sometimes created by microbial activity. Not always, but sometimes. These patterns are ambiguous. They are, in the careful language of astrobiology, potential biosignatures. None of this, individually, is a smoking gun. That is important. A smoking gun would be a fossil, a cell wall, a protein. We do not have that. What we have is context, and the context is getting rich. Stack the findings side by side, and what you get is a planet that had oceans, had lakes, had rivers, had sustained rainfall, had warm conditions, had complex organic molecules, had patterns suggestive of microbial influence, and had all of this happening at roughly the same time that life on Earth was first emerging. Mars, in other words, looks less and less like a barren curiosity, and more like early Earth's twin. A twin that may have gone through the same opening chapters of the same book. And here is where the central thread tightens. because the more plausible Martian life becomes, the more the great filter, the statistical bottleneck that keeps civilizations from spreading across the stars, has to move forward in time. It has to move into our future. It has to move into a region of the pipeline that we have not yet crossed. That is the logic, and it is relentless. Every additional piece of evidence that Mars once hosted life is a piece of evidence that the step called life is easy, and therefore cannot be the thing that explains the great silence above our heads. If Mars was also alive, the problem is not getting life started. The problem is something else. And whatever that something else is, we are probably not past it yet. The tubes sitting in Jezero Crater, then, are not just scientific curiosities. They are instruments in a much larger measurement, an existential measurement. And the answer they return may change everything we think we know about how long our species has left. So what exactly is this silence we keep talking about, and why should a quiet sky above our heads make anyone nervous? Part 5. The universe is too quiet. You have probably heard of the Fermi paradox, but let me give you a version of it that actually lands, because the usual version is too tidy, too classroom. The real version is strange and unsettling. One summer day in 1950, the Italian physicist Enrico Fermi was walking to lunch at Los Alamos with some colleagues. They were talking about UFO reports, as physicists apparently sometimes do, and about the possibility of interstellar travel. They walked, they sat down, they started eating, and then, in the middle of a completely different conversation, Fermi suddenly said, out loud, "Where is everybody?" That one sentence became the seed of one of the most unsettling puzzles in science. Because here is the thing Fermi was thinking about. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. A meaningful fraction of them, possibly most of them, have planets. Astronomers now estimate there may be billions of potentially habitable worlds in our galaxy alone. And our galaxy is roughly 13 billion years old, meaning there has been plenty of time, plenty of raw material, and plenty of locations for life to emerge, evolve, develop intelligence, and spread. Here is what makes it worse. You do not need faster than light travel to colonize a galaxy. You do not need magic. You do not need anti-gravity. If a civilization had even slow, sublight speed probes capable of traveling at, say, 1/10 the speed of light, and those probes could land somewhere, build more of themselves and launch again, a single civilization could seed the entire Milky Way in somewhere between a few million and a few tens of millions of years. That sounds like a long time. It is not. Compared to the age of our galaxy, it is a blink. It is a speck of dust on the face of a clock, which means even if advanced civilizations are rare, even if only 1 in a million habitable worlds produces one, we should still see them. We should see Dyson spheres, partial constructions around distant stars that absorb and re-radiate starlight in characteristic infrared patterns. We should see radio signals, leakage from communications or deliberate beacons. We should see probes in our own solar system. We should see engineered objects crossing the transit-like curves of other stars. We should see evidence that somebody, anybody, has been busy for the past few billion years. We do not see any of this. And that is not a matter of our telescopes being weak. We have looked. We are still looking. The skies in every direction we point are quiet. Not silent at the noise floor. I mean quiet of the kind of unmistakable signatures a galaxy full of civilizations would produce. In 1996, a George Mason University economist named Robin Hanson wrote an essay that tried to turn this silence into mathematics. He called his idea the Great Filter. The basic picture is this. Imagine the development of a galaxy colonizing civilization as a pipeline. At one end of the pipeline is a lifeless planet. At the other end is a civilization that has spread across the stars. In between are a series of steps. The formation of stable planets, the emergence of self-replicating chemistry, the development of single-celled life, the leap from simple cells to complex ones, the emergence of multicellular organisms, the rise of intelligence, the development of technology, the survival of that technological phase long enough to leave the home planet, and eventually the expansion to other star systems. Hansen asked a simple question. If the end of the pipeline is as rare as it appears to be, if we see no galactic civilizations anywhere despite all the time and all the worlds, then somewhere in that pipeline there must be a step that almost nothing gets past. A bottleneck, a great filter, a place where the funnel narrows to almost zero. The silence is not an absence of data. The silence is the data. The silence is telling us that something, somewhere in that pipeline, is stopping civilizations from spreading. Something is preventing them from becoming visible to us. And here is the moment where your stomach should tighten a little, because that something could be behind us, or that something could be ahead of us, and we do not yet know which. If it is behind us, we are the lucky ones, the improbable outliers that made it through some step that almost nothing else got through. If it is ahead of us, we are walking toward a wall that has stopped every civilization that ever got this far, and our children or their children will hit it. So where is it? Where is the step that almost nothing survives, and how is a tube on Mars going to help us find out? Part 6. The Two Doors. Let me put this as starkly as I can, because the core of the argument depends on seeing it clearly. Imagine you are in a hallway, and at the end of the hallway there are two doors, door 1 and door 2. You know, with reasonable confidence, that behind one of these doors is good news, and behind the other is bad news, but you do not know which is which until you open one of them. You also know that once you open a door, you cannot go back. The door you open is the door you walk through. That is roughly the situation we're in with the Great Filter. Door 1 is the door where the filter is behind us. Door 2 is the door where it is ahead. If the filter is behind us, then somewhere in our evolutionary past, we crossed a step so unlikely that almost nothing else in the galaxy has crossed it. Maybe it was a biogenesis, the very first moment when non-living chemistry became living chemistry. Maybe it was the leap from simple cells to complex ones, a step that took billions of years on Earth. Maybe it was the emergence of intelligence. Whichever it was, if the filter is behind us, then we are the rare ones. The galaxy is not empty because civilizations destroy themselves. The galaxy is empty because civilizations almost never get started in the first place, and we happen to be one of the almost nevers. In that scenario, our future is, cosmically speaking, open. There is no wall ahead. The sky's quiet because the road behind us was nearly impossible, and we already walked it. If the filter is ahead of us, the picture flips. Then life is common. Intelligence is common. Civilizations like ours have arisen over and over and over again in the long history of the galaxy. But none of them have spread, because at some point in their development they all hit a wall. They all fail. They all go dark, and the filter that killed them is sitting somewhere in our future, waiting for us to arrive at it. Maybe it is nuclear war. Maybe it is runaway artificial intelligence. Maybe it is climate collapse. Maybe it is something we have not even imagined yet. But whatever it is, it has a very, very good track record. It has never missed. These two scenarios sound like they are about aliens. They are not. They are about us. They are about how much time our species has on the clock. They are about the probability that your grandchildren's grandchildren will exist. Now, the trick in probability theory here is that when you get new evidence, your estimate of which door you're standing in front of shifts. If I tell you that a particular step in the pipeline is easy, then that step cannot be the filter, and the probability that the filter is somewhere else has to increase. If I keep telling you that more and more steps are easy, the probability that the filter is in one of the few remaining steps, many of which may be ahead of us, keeps going up. Think of it like a narrowing lottery. Imagine you bought a ticket and you do not yet know if you won. Someone starts reading the winning numbers, the first few match yours. At first you feel lucky, then you realize with a kind of sick understanding that the more numbers match, the more the eventual mismatch, the one bad number, is going to hurt. Because it is going to be the difference between almost winning and actually winning. The more steps of the pipeline you confirm are easy, the more the remaining uncrossed steps start to look like the one that kills you. We are mid-pipeline. That is the uncomfortable truth. We have crossed abiogenesis. We have crossed the jump to complex cells. We have crossed multicellularity. We have crossed intelligence. We have crossed technology. We're standing somewhere around the middle of Hansen's pipeline, with some steps behind us and some ahead. And the question of which side the filter is on is not academic. It is existential. So how do we test it? How do we figure out which door we're in front of without just waiting to find out the hard way? This is where Mars becomes something more than a planet. Mars becomes the discriminator. Mars becomes the one place we can look within our reach that can give us new data about how easy or hard the early steps in the pipeline really are. And depending on what those 33 tubes contain, the probability distribution across those two doors is going to shift, maybe dramatically in one direction or the other. We are, in other words, about to find out. And the discovery will not announce itself with trumpets. It will arrive as a quiet press release from a laboratory in China, or the United States, or Europe, somewhere in the early 2030s. And the words in that press release will either calm a certain group of philosophers, or scare them half to death. Part 7. Why Mars is the test. Here is why Mars specifically is the test, and why we cannot just learn this from telescopes pointed at distant exoplanets. The central concept you need to grasp is something called independent biogenesis. Biogenesis is just a fancy word for the origin of life. Independent biogenesis means life that got started separately, on its own, without sharing a common ancestor with life somewhere else. Earth has life. Earth's life, all of it, every bacterium, every tree, every whale, every human, traces back to a single common ancestor. We know this because all Earth life uses the same genetic code, the same amino acids, the same chirality, which is the handedness of its molecules. It is all, at the deepest level, one family, one origin event, one biogenesis. Now suppose we find life on Mars. Suppose, when the samples come back, they contain microbes or the fossilized traces of microbes or unambiguous biochemical signatures that cannot be explained any other way. Immediately the question becomes, where did these come from? Are they related to Earth life? Did they share an ancestor? Or did they get started independently? This is not a small question. This is the entire ballgame. Because here is what makes Mars special. Mars and Earth are close neighbours. We can actually test whether Martian life, if it exists, is related to us or not. We can do that by analysing the biochemistry. Does Martian life use DNA or something else? Does it use the same 20 amino acids as Earth life, or a different set? Do its molecules have the same handedness, left-handed amino acids and right-handed sugars, the way ours do? If we find a biology that is different from ours at that level, then it did not come from Earth, and we did not come from it. It is a second, separate origin. And that is the phrase that changes everything. Because if life started twice in a single solar system, twice in neighbouring planets, within a few 100 million years of each other, then life is not rare. Life is ubiquitous. Life is what matter does when you give it warm liquid and time. And if life is ubiquitous, then the origin of life, abiogenesis itself, cannot be the great filter. It cannot be the bottleneck. Because if it were, we would not see it happening twice right next door. And if abiogenesis is not the filter, then the filter has to be somewhere else in the pipeline, somewhere either further along in the biological steps or in the technological ones. And since a lot of the biological steps are behind us, and several are common to both Earth life and Martian life, the probability that the filter is somewhere in the technological steps, the ones we're walking through right now, goes up. That is why a single Martian microbe, or even the fossilized remnants of one, would matter so much. It does not have to be clever. It does not have to be conscious. It does not even have to be alive anymore. It just has to exist, and it has to be independent. And the entire statistical picture of our place in the universe shifts. There is, of course, a caveat. It is called panspermia, and we will come back to it, because it is the one hope that a certain group of scientists are clinging to. Panspermia is the idea that life might have hitchhiked between Earth and Mars billions of years ago, on chunks of rock blasted off one planet by asteroid impacts. If that happened, then Earth life and Martian life might be cousins, not strangers. The same origin event spread across two worlds. In that case, finding life on Mars would not be proof of independent biogenesis. It would just be proof that life, once started, can spread between planets. Which is interesting, but much less cosmically scary. So when the samples come back, the scientists will not just be looking for life. They will be looking for the fingerprints of how different Martian life is from Earth life. They will be comparing biochemistry. They will be comparing chirality. They will be looking at whether the basic molecular toolkit matches ours or deviates in meaningful ways. And out of that comparison, one of a few conclusions will emerge. Either the samples are sterile and the Bostroms of the world exhale, or they contain life that is clearly related to Earth's, and the panspermia door stays open and we stay cautiously uncertain. Or they contain life that is clearly different, independent, separate, and a small group of people around the world quietly close their laptops, step outside, and look up at the sky with a new kind of expression on their faces, because one microbe, truly, one microbe changes everything. So what exactly is Bostrom's full argument? Let's put it all together. Part 8. Bostrom's Logic, fully assembled. Nick Bostrom's essay, the one where the sentence we started with appears, is called Where Are They? And it was published in MIT Technology Review in 2008. It is short, it is accessible, and if you read it, you will come away a little shaken. Let me walk you through his argument step by step, because once you see it assembled, the sentence at the top of this video stops sounding strange and starts sounding, honestly, unavoidable. Step 1. Life got started on Earth. Whatever the origin of life looked like, it happened here. From there, over roughly 4 billion years, it evolved from the simplest replicating molecules to single cells, to complex cells, to multicellular organisms, to intelligent life, to technological civilization. All of these are steps in the pipeline. All of them happened. We are living proof. Step 2. The universe, despite being old and wide and full of potentially habitable worlds, is silent. There are no visible signatures of civilizations, no Dyson spheres on infrared surveys, no artificial signals at any frequency we have searched, no probes in our solar system that we can find, no anomalous transits across other stars, nothing. This silence is a real, measurable thing, and it demands explanation. Step 3. The only way to explain this silence is if something somewhere in the pipeline is filtering civilizations out before they spread. That is the great filter. It is a logical necessity, not a speculation. If the pipeline were easy at every step, the galaxy would be full of civilizations. Since it is not full, at least one step must be very, very hard. Step 4. If we find life on Mars, specifically independent life, then the early steps of the pipeline from lifeless chemistry to single-cellular life must be common. Not unique to Earth, not rare, common. Because if the same thing happened twice on neighbouring planets, it is probably happening all over the galaxy, which means those early steps cannot be the filter. The filter is not behind us, at least not in those steps, which means it has to be somewhere later in the pipeline, and since a lot of the later pipeline is either already crossed by us or in our immediate future, the probability that the filter is in our future goes up. Conclusion. Finding life on Mars would not be good news. It would be evidence that the wall is ahead of us, not behind us. It would be evidence that our chances of becoming a long-lived, stable, spacefaring civilization are worse than we thought. It would be a statistical death sentence whispered rather than shouted, handed to us not by some enemy, but by the universe itself. Now, Bostrom is careful. He is not saying that finding life on Mars would prove the filter is ahead of us. Nothing in probability ever proves anything. He is saying it would shift the probability. It would update our estimate. It would be, as the philosophers say, Bayesian evidence, a nudge in a particular direction. And the direction it nudges us is bad. The subtlety people miss is that this is not a claim about Mars life being dangerous. It is not a warning about alien infection or contamination or invasion. nothing so cinematic. It is purely a claim about what finding life on Mars would tell us about our own statistical position in the history of the galaxy. The microbes themselves could be long dead, fossilized, locked in sealed tubes, utterly inert. It would not matter. The mere fact of their past existence, independent of us, would be enough to make the sky above our heads look colder and our future look shorter. This is why Bostrom wrote what he wrote. This is why a small number of astrobiologists and philosophers and physicists, when they see a new press release hinting at organics in a Martian mudstone, feel something complicated. A mix of scientific excitement and personal dread. They want the truth. They always want the truth. That is what makes them scientists. But some of them are quietly hoping that the truth in this particular case is that Mars is dead. Now you can go back and read the sentence from the beginning. I hope that our Mars probes will discover nothing. Dead rocks and lifeless sands would lift my spirit. It is no longer strange. It is no longer anti-science. It is just a logical consequence of looking at the evidence and following the math. But if the filter is ahead of us, the next question is the one that should really keep you up at night. What is it? What is it that stops civilizations? What is the wall? Part 9. The 2 billion year silence. Before we talk about what might be ahead of us, we have to take a detour through what might be behind us. Because if the great filter is comfortably in our past, the Bostrom argument softens, and there is in fact a candidate for a pass filter that is almost frighteningly good at explaining the silence we see above our heads. It goes back to an Australian physicist named Brandon Carter, who in the 1980s began asking a peculiar question about our position in time. Why, he asked, did it take so long for intelligent life to appear on Earth? Earth is about 4.5 billion years old. Life shows up somewhere around 3.8 billion years ago, but complex life, the kind with cells that have a proper nucleus and internal machinery, life that can eventually build bodies and brains, does not show up until roughly 2 billion years ago, at the earliest. And that is after single-celled life had the entire planet to itself for nearly 2 billion years. Think about that. Almost half the age of our planet was spent in a single-celled stage. 2 billion years of bacteria and archaea, churning through the oceans, building reefs, fiddling with photosynthesis, and never, not once, making the leap to a more complex form of cellular life. That leap, when it finally happened, did not happen many times independently. It seems to have happened once, possibly only once in the entire history of our planet. The biochemist Nick Lane has written extensively about this. His argument in simplified form is that the jump from simple cells, like bacteria, to complex cells, the kind that all animals and plants are made of, required a very strange, very specific event. Namely, one cell, somehow, ended up living inside another cell. The engulfed cell did not get digested. It stuck around. Over enormous spans of time, it evolved into what we now call the mitochondrion, the little power plant that lives inside every one of your cells and makes energy for you. This single event, this merger of two cells into one, may have unlocked the energy budget necessary to build all of complex life. Without it, cells are stuck. They cannot get big. They cannot get sophisticated. They cannot develop the machinery necessary for multicellular life, much less for brains. The British researcher Andrew Watson and his colleagues formalised this kind of reasoning into something called the hard steps model. The idea is that the evolution of intelligence on a planet requires passing through a small number of critical transitions, each of which is extraordinarily unlikely in any given billion-year window. If the transitions are hard enough, and the window of habitability on a planet is only so long, most planets never make it. The stars they orbit go through their main sequences and die before their planets can generate intelligence. If the jump from simple cells to complex ones really is one of those extraordinarily unlikely transitions, then we may have a candidate for the Great Filter, comfortably sitting behind us, roughly 2 billion years ago. In that case, the galaxy might be full of microbes, but nearly devoid of anything more complicated. Mars, in that scenario, could perfectly well have had microbes and never gotten any further. Lots of planets could. The universe would be, in effect, a sea of slime with almost no islands of thought. Now notice what this does to our central story. If the filter is the leap to complex cells, then finding microbes on Mars would not be a disaster. It would be, in a strange way, comforting. It would fit the theory. Microbes are easy, complexity is hard, we got lucky, the filter is behind us, the road ahead is open. But here is the uncomfortable part. The moment we find anything beyond microbes on Mars, or find evidence that Martian microbes were on their way toward complexity, that explanation starts to crumble. And even if we find only microbes, we would still be moving the probability needle. Because microbes on Mars still mean that life itself is common, which means abiogenesis, at minimum, is not the filter, which means the bottleneck has to be at least somewhere further along, which means the filter, though maybe not ahead of us, is closer to us than we thought. And that is before you even ask the more dangerous question. What if there are multiple hard steps? What if 2 billion years of silence on Earth is hiding more than one filter, some of which we still have ahead? This is where the story stops being a debate about ancient history and starts feeling personal, because every additional piece of evidence we collect about Mars, whether microbes or more, or nothing at all, reshapes the curve, and the shape of that curve is, in a very real sense, the shape of our future. Part 10. What if Mars has only microbes? Let's run a scenario in detail because it helps clarify how the reasoning works. Suppose the samples come back in 2031, and the verdict, after years of painstaking laboratory analysis, is that Mars had life. Not complex life. Not fossils of anything resembling an animal or a plant. Not the slightest trace of anything with organs. Just microbes. Simple, prokaryotic, single-celled things, similar in complexity to the Earth bacteria that were around 3 billion years ago. Maybe we see their mineralized remains. Maybe we see clear biochemical signatures, isotopic patterns, lipid membranes, orderly organic sequences that scream biology rather than whisper it. But that is it. Nothing more. What does that mean? On the surface, it sounds like the friendliest version of the discovery. Life, yes, but only the simplest kind. No intelligent Martians, no civilizations, just bugs. The headlines are exciting but not terrifying. The public is thrilled. There is a moment of global wonder, and then life, as it tends to, goes on. But the scientists have to do the math. And when they do, they get a picture that is more interesting than the headlines suggest. If Mars had microbes and nothing more, then one of two things is true. Either Martian life started independently, in which case abiogenesis is easy, and the filter is somewhere later, or Martian life and Earth life are related through panspermia, in which case we learned something about how life can move, but not how common it is. Now assume the first case, independent microbes. What does that tell us? It tells us that the transition from lifeless chemistry to life is not the bottleneck. It tells us that the universe does not have a hard time getting the first step going, which means, looking around the galaxy, a lot of planets probably have microbes, but the galaxy is still silent. We still do not see civilizations, so if microbes are easy, then the filter has to be somewhere between microbes and civilizations, and that could still be behind us, in the leap to complex cells, in the leap to multicellularity, in the leap to intelligence, which would be comforting, or it could still be ahead of us, in some technological phase we have not yet reached or survived, which would not be. In other words, finding only microbes on Mars narrows the search for the filter, but does not by itself tell us where it is. It rules out abiogenesis. It leaves everything else on the table. Now imagine a slightly different scenario. Suppose we find evidence that Mars had not just microbes, but microbes that were showing signs of moving toward complexity. Suppose we find ancient Martian biofilms, layered microbial structures, or hints of cells with the kind of internal organization that on Earth evolved only once and took billions of years. Suddenly the hard steps model starts to look less hard. Suddenly the leap to complexity, the one Nick Lane identified as potentially the filter, looks like something that might happen on multiple planets. And if that is easy, the filter, wherever it is, has moved even further forward, closer to us, into our immediate past, or worse, our future. Every additional thing we learn about Martian life, in other words, pushes the probability of the filter's location. It does not answer the question in one stroke, but it shifts the distribution. And the shift is always, in a certain sense, unfortunate. Because every piece of evidence that a particular step is easy, even if we were the beneficiaries of that ease, pushes the remaining candidate filters closer to our current position in the pipeline. We never get the reassurance that the filter is deep in the past. We only ever get worse news or no news. There is no version of this where learning more makes us feel statistically safer, which is why, quietly, in the corner of the room, the Bostroms of the world keep hoping. Not for ignorance. They want to know. They just hope that the thing we come to know is that Mars is sterile. Because even the friendliest version of finding life there, the just microbes version, is a version where the odds tilt a little against our future. And the worse versions, the ones we need to actually look at now, are where the real nightmares live. Part 11. The real nightmares. So let's talk about what a future filter might actually look like. Because it is easy to hear the phrase great filter and imagine some abstract statistical ghost, some vague concept floating in a philosophy journal, something that happens to theoretical civilizations in theoretical galaxies. That is not what it is. If the filter is ahead of us, it is real. It is specific. It happens to real civilizations, on real planets, around real stars. It has a mechanism. It has a cause. It has a shape you could in principle point at and describe. And the unsettling thing is that when you actually sit down and try to list the things that could plausibly play the role of a civilization-ending wall in our near future, the list is not short. It is not speculative. It is in several cases already sitting in our newspapers. The first candidate and the most obvious one is self-destruction. Civilizations, once they develop advanced technology, gain the ability to destroy themselves. That sounds almost too simple to be profound, but think about what it actually means. For the first 3.9 billion years that life existed on Earth, nothing alive on this planet had the capacity to end itself at a species level. A fire could burn a forest. A virus could thin a population. An asteroid could knock things back by 50 million years. But no creature on this planet could, through its own deliberate actions, make the entire surface of the world unlivable for itself. Then, in a single moment, on a specific day, that changed. On July 16th, 1945, at a place called Trinity Site in New Mexico, a small group of physicists detonated the first nuclear weapon. The device was nicknamed the Gadget. It produced an explosion equivalent to about 21,000 tons of TNT, and in the white flash that followed, the physicist J. Robert Oppenheimer, according to his brother, simply said, "It worked." From that moment on, for the first time in the 4 billion year history of life on Earth, a species had acquired the technical capability to make its own planet uninhabitable for itself. And in the decades that followed, we did not just have the capability, we built the inventory, tens of thousands of warheads dispersed across multiple nations, on missiles, in submarines, in silos, enough firepower to render the surface of our planet hostile to complex life many times over. Now zoom out. Any civilization that reaches the kind of energy and technological capability necessary for interstellar expansion has, by definition, passed through a period where it can destroy itself. You cannot build a starship without mastering the kind of physics that also lets you build a very bad afternoon. If the transition from the self-destruction capable phase to a stable, mature, expansion-ready civilization is unreliable enough, you have a filter. Most civilizations just do not make it. They blow themselves up, or poison their planets, or collapse back into something simpler before they can ever build their first interstellar probe. The galaxy is silent because the talkers kill themselves in the first few centuries of being able to talk. That is one possible reading of the sky above our heads, and if it is the right one, it is not a reading that leaves a lot of room for optimism about where we currently are. Climate collapse is a closely related candidate, and it is worth lingering on it, because it is a filter that does not look dramatic while it is happening. A civilization that advances to industrial or post-industrial technology will almost certainly, in the process, alter the atmosphere and chemistry of its own planet. It will burn things, it will release things, it will change the temperature, the ocean chemistry, the distribution of water, the frequency of storms, the composition of the very air it breathes. On Earth, we are in the middle of doing this right now. Whether we succeed in managing the transition, steering our civilization into a sustainable long-term equilibrium, or whether we fail and watch our societies buckle under the slow accumulated strain of a destabilized climate, is, currently, an open question. Not a settled one, not a hopeless one, but open. Other civilizations elsewhere in the galaxy may have faced exactly the same fork, and many of them may have taken the wrong path. Not in a blaze, just in a slow, miserable slide, food systems breaking, water tables falling, coastal cities retreating, and eventually a civilization that used to build rovers and send them to other planets becomes a civilization that can barely keep the lights on in its own cities. That is a filter too, a quiet one, the kind you die of while still making plans. Then there is artificial intelligence. This is the candidate where, interestingly, Nick Bostrom himself has done some of his most famous work. In 2014, he published a book called Superintelligence, which argued that the development of machine intelligence significantly smarter than humans could represent an existential risk in its own right. The specifics of the argument are technical, but the short version goes like this. A sufficiently advanced AI system, if built without extreme care about its goals and its values, could end up pursuing objectives that are misaligned with human welfare. And because such a system would, by assumption, be smarter than us, it could outmaneuver, outthink, and outweight any attempt we made to correct it after the fact. Bostrom and other researchers have argued that this kind of misaligned superintelligence could be not just a threat to a particular nation or a particular industry, but an extinction-level threat to our entire species. If even a fraction of technological civilizations go through an AI transition and mishandle it, that alone could be a powerful filter. And notice the cruelty of the timing. The same civilizations capable of building starships are also probably capable of building mines, which means, in many cases, the machines arrive before the stars do, and if the machines go badly, the stars never get a visitor. There are also more exotic possibilities, the kind that sound like science fiction until you read the papers. Some physicists have seriously speculated about something called vacuum decay. The idea is that what we think of as the stable vacuum of space, the zero-energy backdrop against which all of reality plays out, might not actually be the lowest energy state possible. It might just be a local minimum. Like a ball resting in a shallow cup on the side of a much deeper valley. If something, anywhere, ever nudged that ball hard enough, the vacuum could decay into a lower energy state, and the transformation would propagate outward at the speed of light, rewriting physics as it went. Everything it touched would be erased, not in flame, not in explosion, just in a quiet, cosmic rewriting of the rules. If any civilization, at any point in the history of our galaxy, discovered the wrong kind of experiment to run, they might not just have ended themselves, they might have ended their entire region of space. We see no such expanding bubbles on the sky, which is either very reassuring because it means nobody has done it yet, or very disturbing because it means the mistake is still out there, waiting to be made, perhaps by us. More mundanely, there are pandemics. Biotechnology, like every technology, cuts both ways. As we gain the ability to read, edit, and engineer biology with increasing precision, we gain, as a side effect, the ability to engineer diseases. A natural pandemic can be terrible, but it is constrained by evolution. A designed pandemic is constrained only by the imagination and carelessness of whoever designed it. A civilization that mishandles that capability, even once, could wipe itself out in months, not centuries. No nuclear detonation required. Just a lab error, or a bad actor, or a piece of research that should never have been done, and that was done anyway because the incentives lined up wrong. That, too, is a filter. Now notice the pattern here. All of these filter candidates share a structure. A civilization advances. It gains capabilities. The capabilities grow, typically exponentially, while the wisdom and the institutions needed to manage those capabilities grow, at best, linearly. At some point, the gap between power and wisdom becomes too wide to bridge. The civilization reaches a threshold where its own tools exceed its ability to handle them, and the civilization fails, not dramatically necessarily, sometimes just quietly. The lights go out, one region at a time, and nobody ever files the interstellar flight plan they were starting to think about. We are in that phase right now. This is not rhetorical. This is a description. We have nuclear weapons and climate disruption, and emerging artificial intelligence, and rapidly advancing biotechnology, and increasingly sophisticated cyber infrastructure, and we have all of it happening at the same time in the same century, on a planet whose political institutions were largely designed in the 18th and 19th centuries by people who had never heard of a nuclear warhead or a neural network or a genome sequencer. We are, by any reasonable assessment, inside the danger zone, not approaching it, inside it. Our parents were born into it, and our children will be born further into it, and the only real question is whether any generation of ours will be born on the other side of it. And here is the specific way this connects back to Mars. If the tubes come home and they contain independent life, then the conclusion we draw is not that aliens are coming for us. There is no invasion fleet. There is no infection. The conclusion is colder and more abstract than that. It is a conclusion about population statistics. It is this. If life started independently on both Earth and Mars, then civilizations like ours must have arisen many, many times before, in many, many places, around many, many stars, across the long billions of years of our galaxy's history. And since we see none of them, since the sky above us is genuinely quiet, something in the pipeline between microbe and starfarer is killing them. And we, sitting here in our particular dangerous century, holding nuclear codes and training ever larger AI systems and watching our climate shift, are plausibly facing whatever it is right now. We do not necessarily know its name, but we are probably in the same room with it. The Fermi silence in this reading is not empty. It is a graveyard. And the absence of voices above our heads is not because nobody ever spoke. It is because almost everyone who ever tried to speak was silenced before they could be heard. The galaxy is not a vacant stadium. It is a stadium full of people whose microphones were cut before they could finish their sentences. That is the weight sitting inside those 33 titanium tubes on the surface of Mars. Not germs, not infection, not some creature feature fear of alien contamination. Just numbers, just statistics, just a set of molecular fingerprints that could, in the right combination, tell us that we are almost certainly walking towards something, and that we do not yet know what. And the people who take this reasoning seriously are not paranoid. They are just following the logic through to its conclusion, and not flinching at what it implies about the road ahead. So is there any way out of this? Any scenario where finding life on Mars does not carry this terrible statistical weight? Any version of the coming decade where the tubes come back, and the news is remarkable, and yet our future stays intact? There is, actually, one. A narrow one, a fragile one, and we should talk about it. Part 12. The One Escape Hatch. There is one scenario, and only one, in which finding life on Mars does not push the great filter ahead of us. One narrow door. One escape hatch. One way the tubes could come back positive and the universe could still be statistically the kind of universe we want to live in. And that scenario has a strange, almost poetic name. It is called panspermia. The idea itself is simple, even though the word sounds intimidating. Earth and Mars have been trading material with each other for billions of years. They are neighbours in the same solar system, and neighbours, over cosmic time, share things whether they mean to or not. Every so often, a large asteroid or comet hits one of the planets, and the impact is energetic enough to blast rocks off the surface and send them tumbling into interplanetary space at speeds high enough to escape the planet's gravity entirely. Some of those rocks then drift for thousands or millions of years through the vacuum, getting slowly nudged by the gravity of the Sun and the other planets, until eventually a small fraction of them happen to fall onto the other world. It is a slow, patient exchange, not a river of traffic, more like a handful of postcards arriving centuries apart mailed by accident. We know this actually happens because we have found pieces of Mars here on Earth. You can hold them in your hand under the right conditions. They sit in museum drawers and in university geology departments around the world. We identify them as Martian because the gas trapped in tiny bubbles inside them has exactly the isotopic signature of the Martian atmosphere, measured directly by Viking and Curiosity and other missions. Chemistry does not lie. These are pieces of another world sitting on this one. They got here by travelling across millions of miles of empty space after being hurled off the surface of Mars by some ancient, violent impact, and eventually landing somewhere on Earth, usually in a cold, dry place like Antarctica, where they can be spotted against the ice. The most famous of these meteorites is a rock called ALH 84001. It was discovered in Antarctica in 1984 as part of the Allen Hills meteorite collection, and for more than a decade it sat quietly in storage without anyone realizing how famous it was about to become. Then, in 1996, a group of NASA scientists announced that when they had examined the interior of the rock under powerful microscopes, they had seen tiny, worm-like structures that looked, at least superficially, like fossilized microorganisms. The announcement was so significant that the President of the United States at the time made a televised statement about it. The world paused briefly to consider the possibility that we had found evidence of ancient Martian life sitting in a laboratory on Earth. Then the scientific community did what it does. It pushed back. Other researchers examined the same rock, ran their own analyses, and pointed out that the structures in question could plausibly be explained by non-biological processes: crystal growth, mineral deposition, contamination during the rock's long stay on Earth. The claims got quieter over the years. They were never fully disproven. They were also never fully confirmed. The consensus settled somewhere around interesting, but not a smoking gun. But the meteorite itself is real. It did come from Mars. It is sitting somewhere right now, still being occasionally poked at by scientists with new instruments, quietly refusing to give up a definitive answer. And here is why ALH 84001 and the other Martian meteorites like it matter for our story. They prove the delivery mechanism. They prove that rocks can make the trip. They prove that material from one planet in our solar system routinely ends up on the other. The question for panspermia is not whether rocks can travel. That question is settled. The question is whether something alive can travel inside one of those rocks and survive the journey. So imagine the scenario. Suppose, 3 or 4 billion years ago, microbial life existed on one of the two planets. It does not matter which one for the logic of the argument. Call it Earth, for concreteness, though Mars actually cooled and became habitable earlier than Earth did, so in some versions of this story, Mars is the sender and Earth is the receiver. Either way, suppose there is life on one of them, a major asteroid hits. Chunks of surface rock get blown into space, carrying, deep in their fractured interiors, shielded from the worst of the heat, colonies of microbes. Those rocks then drift through space for thousands or millions of years. The microbes inside them face vacuum, cold, radiation, starvation. Then, eventually the rock's orbit intersects the other planet. Fiery atmospheric entry, impact, and the outside of the rock burns away, but the inside, the deep inside, stays intact. The microbes inside, if any are still alive, get deposited onto the new world. They find conditions they can tolerate. They multiply. And life now exists on 2 planets, not because it started twice, but because it started once and moved. If this actually happened, then Earth life and Martian life would not be independent origins at all. They would be distant cousins, siblings separated by millions of years of different evolutionary pressures on different worlds, but sharing a common ancestor somewhere back in the deep dark of the early solar system. One origin event, 2 worlds. And this is where the statistical implications of the discovery would be very, very different from the nightmare scenario. Because if Martian life is our cousin, then finding it does not prove that abiogenesis is easy. It does not prove that life starts all over the galaxy. It just proves that life, once it starts in a particular solar system, can spread within that system. Which is a fascinating fact about biology and about the hardiness of microbes, but it is not a fact that tells us the great filter is ahead of us. The sample size is still 1. The origin of life as an event still happened only once that we can prove. The bottleneck could still be right there, in that first impossibly unlikely transition from chemistry to biology. And we, as the products of that singular event, could still be the lucky ones, the improbable outliers, the descendants of the 1 in a trillion role that made life possible in this solar system, and, for all we know, in very few others. So how would we actually know? How would we distinguish between a Martian life that is truly independent of us and a Martian life that is our distant cousin? The answer is that the samples themselves would tell us. This is why the laboratory analysis of the returned material is going to be such an enormously detailed, painstaking process. Scientists will not just be asking, is it alive or was it alive? They will be asking, what is it made of, at the deepest molecular level, and they will be comparing that answer to the corresponding facts about life on Earth. There are a few key things they will look at. The first is the genetic code. All life on Earth uses DNA, organised in a specific way, with a specific set of base pairs and a specific set of rules for translating those bases into amino acids. If Martian life uses DNA, or a close variant, arranged in a similar way, the simplest explanation is common ancestry. The second is the set of amino acids used to build proteins. Earth life uses 20 specific amino acids, selected from a much larger set of chemically possible ones. If Martian life uses the same 20, that is not a coincidence. That is a fingerprint. The third is chirality, which is the handedness of the molecules involved. This is the subtle one. It turns out that many organic molecules come in 2 mirror image versions of themselves, a left-handed form and a right-handed form, chemically identical in most ways but geometrically opposite. On Earth, life almost exclusively uses left-handed amino acids and right-handed sugars. There is no deep chemical reason for this. It is more or less an accident of early biological history, but it is a universal accident across all known life on this planet. If Martian life uses the same handedness as Earth life, that is a powerful piece of evidence for shared ancestry. If Martian life uses the opposite handedness, or a random mix, then it clearly did not come from the same source we did. The scientists will be making all of these comparisons and more. They will be looking at lipid structures, metabolic pathways, the detailed chemistry of whatever cellular membranes they find. Each piece of data either nudges the probability toward shared ancestry or toward independent origin. And when enough data has been collected, a verdict will emerge. If the verdict is shared ancestry, panspermia becomes the leading explanation. The Bostroms of the world exhale, at least partially. The universe, as far as we can tell, is still the kind of universe in which life getting started may be genuinely rare, and we may genuinely have time, not certainty, never certainty. But at least the worst of the statistical bad news is deferred. If the verdict is independent origin, with different chirality, different amino acids, different molecular architecture, then panspermia is ruled out as the explanation. 2 origins. The bad door. The one Bostrom was praying we would not walk through. There is, however, reason to be cautious before we lean too hard on panspermia as our escape hatch. because the conditions required for it to actually work are genuinely demanding. A rock has to be blasted into space with enough force to escape the planet's gravity, which means surviving a shockwave that would vaporize most things. It has to be large enough that the microbes sheltered deep inside are insulated from the heat of the impact. It has to drift through interplanetary space for potentially millions of years, during which time any microbes inside it are exposed to cosmic radiation, extreme cold, and zero pressure. It has to survive entry through the other planet's atmosphere without burning to a fine dust, and the microbes inside it have to still be viable when the rock finally comes to rest. Then they have to find themselves in a local environment on the new planet that is hospitable enough for them to start multiplying rather than simply dying in an unfamiliar place. It is not impossible. Some microbes are genuinely astonishing in their resilience. Certain bacteria can survive in space, in vacuum, in extreme radiation, in conditions that would kill almost anything else. But not all microbes are that tough, and not all journeys leave any of the cargo alive. Panspermia is not automatic. It is not guaranteed. It is a physically possible scenario, but it is not a physically necessary one. And even if some exchange of material did happen between Earth and Mars, the probability that it happened in just the right way, at just the right time, with just the right microbes, to establish a connected biology on both planets, rather than independent origins that merely happen to occur around the same cosmic epoch, is uncertain. It is the difference between two siblings and two strangers who happen to show up at the same party. Hard to tell which one you're looking at from the outside. You have to check the DNA. So panspermia is a hope, a real one, a scientifically respectable one, but a fragile one. It is the single narrow path by which the discovery of Martian life does not mean what Nick Bostrom fears it means. It is the one way the tubes could come back positive and still leave the future open. One thread, holding up a version of the universe in which our species is not statistically doomed. Keep this in mind, because when the samples arrive and the laboratories begin their analysis, the news will come out in fragments. Organic molecules confirmed, isotope ratios measured, possible biosignatures under review. And somewhere in the middle of that long, patient stream of reports, a specific comparison will quietly be made between Martian biology and our own. Same code or different. Same handedness or different. Same amino acids or different. And the outcome of that comparison, more than any other single piece of information that will come out of this entire mission, will tell you which kind of universe you have been living in the whole time. If they are related, we have time. If they are not, we probably don't. Part 13. The day the answer arrives. Let's do something speculative but grounded, because I think it helps you actually feel what is coming. Not just understand it as an argument, not just follow the statistics, feel it. Let me take you forward in time to a day that will almost certainly occur, somewhere around 2031 or shortly after, in a conference room in Beijing, or Pasadena, or Paris, or possibly all three at once, in a coordinated announcement that has been planned for months behind the scenes. Picture the room, a press conference, a long table, covered in one of those plain cloths that space agencies always seem to use, probably blue or black, with a logo printed at regular intervals along the front edge. Microphones. A row of scientists in slightly rumpled jackets, who have not slept much in the last several weeks, because the final rounds of peer review on the paper were brutal, and everyone wanted to be absolutely certain before going public. A logo backdrop for whichever space agency is hosting. A moderator standing to the side, clipboard in hand, quietly managing the flow. Cameras at the back of the room. Flash bulbs, which no longer really flash because cameras are all digital now, but the reflex remains. You still see the little pulse of LED lights. The shutter clicks are still simulated because humans apparently need the sound. The moderator introduces the speakers. There are usually 3 or 4 of them. A senior administrator whose job is mostly to thank people and set the tone. A lead scientist, the person who actually knows the details. A biochemist who will handle the technical questions. sometimes a philosopher or a policy person, tacked on at the end, there to say something thoughtful about meaning. The lead scientist steps forward, adjusts the microphone, clears their throat, looks at the first slide. What they say in the next 90 seconds depends on the universe we live in. In one version of this moment, they say that after years of analysis across multiple laboratories on multiple continents, the samples returned from Mars show no evidence of past or present life. No organic biosignatures that cannot be explained by ordinary abiotic chemistry. No isotopic anomalies that demand a biological interpretation. No structures at the microscopic scale that resemble anything cellular. No lipid residues. No chirality bias. Nothing. Mars, it seems, was habitable once. Genuinely habitable. With liquid water and rich chemistry and sustained warm periods. But it was never inhabited. Every door the scientists opened, they found empty rooms. The headlines the next day will be sober, disappointed, in a muted, grown-up sort of way. A kind of collective global sigh. A few think pieces about what it means to discover that we might be truly alone. Some religious writers will find it meaningful in their own way. Some atheists will find it meaningful in theirs. The quest continues, the articles will say. Europa awaits, under its shell of ice, with its possible subsurface ocean. Titan awaits, with its lakes of liquid methane and its strange prebiotic chemistry. Enceladus awaits, spraying plumes of water from its south pole. But Mars apparently is sterile, a beautiful, tragic, empty place. In that version of the day, Nick Bostrom and a quiet handful of others take their drinks a little slower that night. Not because they got what they wanted in a gleeful sense. Nobody in that group is cackling. They did not want disappointment. They wanted data. They are scientists and philosophers first, and people second, and the whole point of their worldview is that you look at what is actually there, whatever it happens to be. But the data, in this particular case, tilts the probability back toward the comforting door. The filter might well be behind us. A biogenesis on Earth might genuinely be a fluke. The quiet above our heads might simply mean that getting started is hard, that the transition from chemistry to self-replicating biology is so unlikely that in a typical solar system it just does not happen, and that we are one of the very rare places where it did. And in that world the future remains open. The road ahead is long. Our species has time, maybe a lot of it. They will not say any of this out loud at the press conference. They will not call a radio station. They will probably just make themselves a late dinner, sit down with a glass of something, and feel quietly a little less afraid of the sky. In the other version of this moment, the scientists say something very different. They say that the samples contain clear, multiply-confirmed biosignatures. Organic molecules in patterns that cannot be explained abiotically, verified across multiple independent laboratories using multiple independent methods. Isotopic ratios consistent with biological fractionation, the specific way living processes prefer lighter isotopes when they build their molecules, a fingerprint of metabolism. Fossilized structures at the microscopic scale that match nothing in the abiotic catalogue, shapes that have organization and regularity that chemistry alone does not produce, and most importantly a biochemistry that is subtly but clearly different from our own, a different set of amino acids, outside the 20 that all Earth life uses, a different chirality, possibly a mixture, possibly the opposite of ours, different molecular structures at the most fundamental level of the cellular toolkit. Life, they will say, arose independently on Mars. That is the version of the moment the people we have been talking about this whole time are dreading. Not because microbes are scary, not because they are worried about contamination, but because of what that specific sentence, independent origin, means for the statistics of the galaxy and for the length of the road ahead of us. And here is the thing that makes it strange, the thing that almost nobody talking about these scenarios ever captures correctly. The atmosphere in that room, if this is the day that happens, will probably not be panic. It will not be doom. It will not look like a scene from a movie. No one will be crying. No one will be shouting. The lead scientist will not slam their hand on the table, On the surface, the mood in the room will actually be triumphant. Applause. Genuine, sustained applause. That kind of ripple that moves across a press corps when they realise they are witnessing something historic. Statements about a historic day for humanity. Quotes pre-written and released to the evening news. The lead scientist, who knows exactly what they have found, will speak in measured, careful tones about the implications. They will use phrases like, "We are still at the beginning of understanding what this means, and further work is needed to establish the full context of the discovery." The audience will cheer. The anchors on the evening news will start their broadcast with the word "finally." Children at home will be told that humans found proof we are not alone in the universe. Social media will explode with wonder and memes and speculation and conspiracy theories and heartfelt posts about how this changes everything. But in that audience, in that press room, somewhere along the wall, a certain kind of person will be unusually still, not horrified, not crying, just still. They will be thinking. They might be running numbers in their head. They might be mentally rewriting the paper they were planning to publish next year. They might just be watching the reactions of the people around them with a quiet, almost clinical sadness, because they understand something that the room, in its celebration, does not yet understand. And that understanding will not make them feel superior. It will just make them feel heavy. Over the next several days, in long-form essays in scientific publications and philosophical journals and the better corners of the internet, the second wave of coverage will begin. Not the breathless, wondrous first wave, the second, slower one. The Bostrom logic quietly and patiently laid out step by step for a public that has never heard of it before. The great filter explained from scratch, the pipeline, the two doors, the statistical update, the meaning of that specific phrase, independent origin, not for Mars but for us. There will be podcasts. There will be interviews with philosophers who have been waiting 30 years for someone to ask them about this. There will be a new book deal or two. Some of the better science communicators will do their job and walk their audiences through the argument with care. Some of the worse ones will turn it into a scare story, which is not the same thing and does more harm than good. That is always how it goes, and most people will not notice. Most people will absorb the initial wonder and then move on. The story of a new microbe on Mars will be fascinating for a week or two, and then recede into the background noise of ordinary life. Because people have bills and kids and jobs and commutes and medical appointments and bad weather and dinner to cook. That is fine. That is normal. That is how every major scientific shift actually lands in the world. Not with a single dramatic reckoning that reshapes society overnight, but with a long, slow sifting into the collective unconscious, where the knowledge settles over years, shaping fiction and policy and art and private thought in ways that only become visible in retrospect. But for those who do notice, for those who follow the logic all the way through to its conclusion, for those who understand what that phrase, independent origin, actually means about the galaxy and our place in it, for them, something will shift quietly, and it will not shift back. It will not be a panic. It will be a reorientation, a quiet one, a permanent one. They will still make breakfast the next morning. They will still go to work. They will still love their families and argue with their neighbours and feel small pleasures and small irritations and live their lives in most of the ways they always did. But underneath all of it, there will be a new awareness, a new weight, a new dimension of meaning attached to certain kinds of news stories. Every time they see a headline about nuclear tensions or about climate records, or about the latest advance in artificial intelligence, they will feel, in a way they did not before, the presence of the filter. They will sense the narrowing of the corridor. They will understand, at a level that most people never will, why certain institutional choices matter, why certain kinds of research feel urgent, why certain warnings deserve to be taken seriously. Because the meaning of that moment, if it comes, is not really about Mars at all. Mars, in a way, is almost incidental. Mars is the messenger. The message is about us, about the rest of the numbers on our cosmic lottery ticket, about the steps remaining in the pipeline, the ones we have not yet crossed, the ones where the filter might still be hiding, and more of those numbers, with that single announcement, with that single phrase uttered by a tired scientist in a slightly rumpled jacket under the lights of a coordinated press conference, will suddenly have turned out to match, which is exciting when you're playing a lottery you want to win, and less exciting when the lottery is actually a countdown, and matching too many numbers means you are closer to the thing at the other end of it than you thought you were. That is the version of the day some people are quietly hoping never arrives. Not because they fear the microbes, but because they fear what the microbes, by merely existing, would be telling us about ourselves. Part 14. The meaning of that moment. Let me pull this out and say it plainly, because the weight of it sneaks up on people, and I do not want it to sneak up on you. I want you to see it coming, so that when the day arrives, if it arrives, you are not caught off guard. If we find an independent origin of life on Mars, the first thing we learn is that life is common in the universe. Not possible, not theoretically possible under the right conditions, given enough time, with enough luck. Common. Because if it happened twice in a single solar system, on two neighbouring worlds within a few 100 million miles of each other, within a few 100 million years of each other, geologically speaking, almost the same afternoon, then across the hundreds of billions of stars and trillions of planets in our galaxy alone, it is almost certainly happening constantly. It has been happening for more than 10 billion years. The universe is, in that scenario, teeming. The oceans of countless worlds have pulsed with microbial life, bloomed, crashed, bloomed again, gone dark, restarted somewhere else. Life, under that reading, is not a miracle. Life is what matter does when you give it warm liquid and time. Life is the rule, not the exception. That sounds, on the surface, like wonderful news. And in one sense, it is. It is the answer to a question our species has been asking as long as we have had language to ask it. Are we alone? No, we are not. We are one of many. But then the second thing we learn. The second thing is harder, because it is a thing we learn not by looking at Mars, but by looking at the sky and noticing what we do not see. Civilizations are not common. If they were common, they would be loud. They would be visible. They would be building things, spreading things, powering things, sending things. They would be reshaping their solar systems in ways we could detect with telescopes. They would be leaking radio noise into the galaxy. They would have sent probes through our neighbourhood by now. They have not. The sky is quiet, genuinely, measurably quiet, which means somewhere between common microbes and rare civilizations there is a gap. And that gap, whatever its shape, whatever its mechanism, is the thing we have been calling the Great Filter. If microbes are easy, and we are looking around at a silent sky, then the filter lies somewhere between the microbial stage and the galactic expansion stage. That is a large chunk of pipeline. Some of it is behind us. Some of it conceivably could be in front of us. We cannot tell exactly where it is from one data point. We cannot point at one step and say, here, this is the wall, this is where everyone dies. But the discovery of independent Martian life would, in one stroke, eliminate from consideration an entire category of filter candidates. The earlier steps, the chemistry to biology step. It is a miracle that life started at all step. And that is the category where it was most comforting to have the filter. Because if the filter is way back there, we are safe. We already walked through it. We do not have to do anything. The rest of the road is open. Think about it this way, because I think it helps. There are essentially two ways for a civilization to be rare. The first is that getting to civilization is hard. The second is that staying as a civilization is hard. Those are not the same thing, and they have very, very different implications for us. The first is comforting. If it is hard to get here, if the odds against ever producing a thinking, tool-using, language-speaking species on any given planet are astronomical, then once you're here, you might have a long run ahead of you. You have done the hard part. You can settle in. You can build. You can look forward. The second is frightening. If it is hard to stay, if civilizations reliably appear and then reliably destroy themselves or collapse or go dark, then here, right now, at the moment of peak capability and peak fragility, is exactly the place where you face your worst odds. You're not past the filter, you're standing in it. Independent Martian life takes a giant chunk out of the first option. It says no, getting started is not hard. Getting from lifeless chemistry to life is easy. Mars did it. Earth did it. Lots of planets probably did it. Lots of planets are probably doing it right now. And lots more did it billions of years ago on worlds whose stars have since burned out. So if civilizations are still rare, it is not because the beginning of life is the bottleneck. It is because something along the way is trimming civilizations out of the galaxy. Not at the start, somewhere in the middle, or worse, toward the end. Somewhere in the steps that we are either in the middle of or have just completed. Statistically, when you find out that one more box can be checked in the easy column, the boxes left unchecked, the ones that could still contain the filter, each get a larger share of the probability. Imagine a suspect list with 10 names on it. A detective walks in and eliminates 2 of them. They have alibis. They are cleared. The other 8 suddenly each look more likely. Not because any new evidence appeared against any of them, just because the probability mass got redistributed. That is what Martian life does to the suspect list of possible filters. It does not accuse any one of them specifically, but it raises the odds on all the remaining candidates, including the ones that lie in our future. The nuclear candidate, the climate candidate, the artificial intelligence candidate, the pandemic candidate, the unknown candidate. They all get a little more probable all at once with a single press conference. The discovery, in other words, is really about humanity, not about Mars. The microbes themselves are almost a detail, a lovely detail, an astonishing detail. The kind of detail we will put in textbooks and museums and children's books for the next 1,000 years, if we have a next 1,000 years. But the real lesson of the discovery is statistical. The real lesson is about us, about our position on the pipeline, about how many steps we have left, and how dangerous those remaining steps are likely to be. For a while, nothing will feel different. That is the strange part. You will still get up in the morning and drink your coffee and scroll your phone and go to work or school. The discovery will be a curiosity, a talking point, a bumper sticker, a documentary you watch half of before falling asleep. Then, in the background, over months and then years, the implications will slowly settle into certain parts of the culture. Philosophers will write about it. Novelists will work it into their plots. Religious thinkers will have to account for it, to reconcile their traditions with a cosmos that apparently grows life the way other places grow weeds. Policymakers eventually will notice it. And somewhere, in the quiet interior rooms where governments think about the very long term, the rooms most people do not even know exist, someone will put on a slide that says something like, "The expected lifetime of technological civilizations is shorter than we previously modelled," and the room will not panic. There will be no shouting, no one will storm out. The room will just get a little quieter, a little more serious, a little more willing to fund certain things, a little less willing to ignore certain others. Budget lines that used to lose out will start winning. Arguments that used to sound paranoid will start sounding prudent. That is how existential shifts actually land. Not with a thunderclap, not with a single day that changes everything. With a long, slow exhale spread across years, and a quiet re-evaluation of what this century is actually for. A re-evaluation that most people will never consciously notice, but that will, in small increments, reshape the priorities of the species, and all of it triggered by a handful of molecules in a tube on a planet we almost did not visit. Part 15. Why some scientists hope for nothing. Now, we can return to the sentence we started with and really understand it, properly this time, with all the context behind it. Nick Bostrom, back in 2008, wrote that he hoped our Mars probes would discover nothing. Dead rocks and lifeless sands would lift his spirit. At the very beginning of this video, hours ago now when you first heard that sentence, it probably sounded contrarian. Maybe even a little grumpy, or a little anti-science, or a little odd coming from a man whose entire life's work is humanity's long-term future. It might have sounded like the kind of thing you read and shake your head at, Because obviously finding life beyond Earth would be one of the greatest discoveries in the history of our species, and obviously anyone who says otherwise must be missing something. Now, I hope that same sentence lands very differently. I hope it lands as the quiet, careful, deeply considered statement of someone who has actually done the math and is brave enough to tell you what the math says. Because he is not, in any meaningful sense, anti-discovery. He is not hoping we stop looking. He is not afraid of Mars or of aliens or of the science itself. He is not some reclusive pessimist sitting in a tower at Oxford, wishing humanity would stop exploring. The opposite. He has spent decades thinking about humanity's future. He has written books and papers about the things that could end us, the things that could save us, the technologies that could reshape us. He cares, maybe more than almost anyone else alive, about us making it through the next few centuries. What he is doing when he writes that sentence is the thing philosophers are trained to do, which is to carry the logic all the way to its uncomfortable conclusion and not flinch when it gets there. The logic says this: if life turns out to be common in the universe, then civilizations like ours statistically are not, and we are a civilization like ours, which means our odds, on the longest timescales, are worse than we might hope, which means his work, the work of humanity's future, is more urgent than the cheerful version of reality might suggest. If life is everywhere and civilizations are rare, then the thing that keeps civilizations rare is still out there in our near future, waiting, and we should be spending more time and more money and more attention figuring out what it is and how to avoid it. That is not pessimism. That is the correct response to the evidence, if the evidence points that way. So when Bostrom writes that he hopes for nothing on Mars, he is writing as someone who wants humanity to have a long future. That is the point. That is the whole point. He sees in the possibility of Martian life a piece of evidence that would shorten that future in probability, that would compress the expected lifetime of our species, and he would rather live in the version of the universe where that evidence does not appear. It is not a fear of microbes. It is not a phobia of discovery. It is not some irrational cringe at the thought of finding something out there. It is simply a preference, at the level of cosmic statistics, for one kind of universe over another. A universe where getting started is hard, where we are rare, where the road ahead of us is long and open. Over a universe where getting started is easy, where we are common, where the road ahead is narrowing faster than we thought. Put like that, hoping for a sterile Mars is not anti-science. It is the opposite of anti-science. It is taking science so seriously that you let its full conclusions reach you, even the ones that make you wince, even the ones that land in your stomach and stay there. It is saying, I understand what this evidence would mean if we found it, and I do not want that meaning to be true, because that meaning is bad for us, for my children, for my grandchildren, for everyone alive right now, and everyone who might otherwise have been born in the centuries ahead. That is not cowardice. That is not wishful thinking. That is a very particular kind of intellectual honesty, the kind that admits that sometimes the answers you are most hoping for scientifically are not the answers that would serve you best personally. You will notice that this is a minority view. Most scientists, when asked, still say they hope we find life on Mars. Most of them, when they say that, are not thinking about the Fermi paradox or the Great Filter or Robin Hansen's 1996 essay. They are thinking about the wonder of the discovery itself, about the scientific value, about the answer to a question our species has been asking since we first looked up at the night sky and wondered who else might be looking back. And that is a perfectly reasonable thing to hope for. There is nothing wrong with it. In fact, there is something beautiful about it, something that speaks to the better parts of our curiosity as a species. I do not want to disparage that hope. I share it, honestly, in a way. Most of us do. But a minority, the Bostroms and a scattered company of astrobiologists and physicists and philosophers who take the statistical reasoning seriously, cannot quite share that hope without an asterisk. A quiet one. They want the truth. They always want the truth, whatever it is. That is what makes them scientists. That is the whole job. But they understand that a particular kind of truth, The independent Martian biology truth carries a bill attached to it. A bill paid not in dollars or disappointment, but in our expected future. A bill that, if it came due, would be the most expensive thing our species ever signed up for. And it is a bill you would rather not receive, even if you would accept it honourably if it arrived. Most of these people do not say this out loud, at least not at dinner parties, not at conferences, at least not in the keynote sessions, not in the television interviews, because it sounds, at first blush, like they are hoping for scientific failure, which is almost the worst thing a scientist can appear to be hoping for. They are not. They are hoping for a particular answer to a particular question. And they are fully willing to be told that their hope was misplaced, because that is how science works, and they know it. But they suspect correctly that if they spelled out their reasoning in casual conversation, in the wrong room, to the wrong audience, they would end up sounding like pessimists or contrarians or kooks, when in fact they are simply people who have followed the math all the way through to its conclusion and arrived at a quiet, uncomfortable, rational preference for an emptier universe. If you take one thing away from this entire story, let it be this. More life is not necessarily better news. Fewer other civilizations is not necessarily worse news. The universe we would prefer to live in, if we genuinely care about our own long-term survival, is probably not the teeming, crowded, bustling universe of our science fiction. The universe full of alien federations and galactic councils and worlds around every star, it is probably the lonelier one, the rarer one, the one where getting to where we are was genuinely hard, and where, therefore, we have earned some measure of cosmic breathing room, where the silence above our heads is not a warning, but a long, open runway. The people hoping for emptiness are not hoping to be alone. They are hoping to have time. They are hoping that our story as a species is not one of many thousands of identical short stories scattered across the galaxy, each one ending quietly before its characters could ever reach the next star. They are hoping it is something stranger and more precious. A story that took an unlikely amount of time and an unlikely number of chance events to even begin, and that, precisely because of that unlikeliness, has room to continue for a very, very long time. And the instrument that will soon tell us which kind of story we are living in is already in place. It is sitting on Mars right now, in the form of 33 titanium tubes, each about the size of a cigar, under a thin pink sky, on the floor of a crater that used to be a lake, in the dust of a world that, depending on what those tubes contain, is either our quiet, dead neighbour, or the second chapter of a much larger, much older, much more frightening book. Part 16. The Tube in the Dark. Let me take you back there, one more time. Close your eyes for a second, if it is safe to do so, and picture it. A crater, about 28 miles wide, on the surface of a planet that is, at this moment, roughly 150 million miles away from you. The sky above the crater is a dusty salmon pink during the day, and a dim, star-specked darkness at night. The air is thin, less than 1% the pressure of Earth's atmosphere, and mostly carbon dioxide. The temperature can drop to minus 140 degrees Fahrenheit on a winter night and rise to a chilly midday high when the sun hits at just the right angle. There is wind. There is dust. There is occasionally weather. On the floor of that crater, in a carefully chosen cache site, sits one of the tubes. A small titanium cylinder, about 6 inches long, sealed against contamination. Inside it, some grams of Martian rock, drilled from an outcrop that once lay underwater, now lies exposed to the cold, the radiation, the slow grinding of time. The tube does nothing. It sits there. It is acted upon by nothing except the occasional gust of wind sliding thin dust across its surface. There is no ceremony. There is no attention. It is a small piece of engineering waiting. Whatever is inside it now. That is the part that almost nobody stops to appreciate. The answer is already there. The molecules in that tube are not waiting to become something. They are something. They have been whatever they are for perhaps 3 billion years, and they have been sealed, as they are now, since the Perseverance rover drilled them and closed them in. The question of whether Mars had independent life, is not a future question. It is a present fact, already written into the chemistry of those rocks. We just have not read it yet. That is the strangest part of this whole story, when you let it sit with you. The universe right now already knows the answer. The answer is encoded in specific molecules in specific tubes, sitting on specific patches of specific crater. We do not have to do anything to the universe to change that answer. We just have to go pick up the tubes, carry them home and analyze them. And whatever the answer is, it has been true the entire time. If Mars has independent life, it has had independent life the entire history of modern humanity. It had independent life while the pyramids were being built, while the Roman Empire rose and fell, while your grandparents were born, while you were in school, while you were watching this right now. It has been sitting there, undisturbed, unmeasured, unread, while every philosopher from Plato to Bostrom argued about our place in the cosmos. The universe has not been keeping a secret. It has just been waiting for us to come and look. In that way, the tube is a small, perfect mirror of the larger silence above our heads. The sky is not quiet because there is no answer. The sky is quiet because we have not yet gotten close enough to whatever answer it contains. The Fermi paradox is not a mystery of absence. It is a measurement with data we cannot yet fully read. Somewhere in the long history of the galaxy, civilizations either spread and are visible, or they do not, and they are silent. The record either way is out there. We have just not walked far enough into the dark to read it. And yet here is the thing. We are about to walk a little further. Within the next decade, probably, those tubes will be on a ship back to Earth. Within a little longer than that, they will be in laboratories, under mass spectrometers, under electron microscopes, being analysed at a resolution that no Mars rover could ever achieve. And whatever the tubes contain, it is going to come out. The answer has a deadline now, not a certain one. Things can slip. Missions can be delayed, budgets can be cut, but the momentum is there. The samples are going to come back. The analysis is going to happen. The answer, whatever it is going to be known. In some ways, it is already inside us. The molecules in those tubes, the specific patterns of carbon and hydrogen and oxygen and trace metals, are already a completed message. The cosmos has already written it. We just have not read the last page yet. And the last page may be short, just a few lines. Either, no, Mars was always empty, and our species has every reason to believe the road ahead is open. Or, yes, Mars had its own life, separate from ours, and our species has to reckon with the fact that every other story like ours seems to have ended before it could speak to the stars. Nick Bostrom does not know which page is coming. Neither do I. Neither do you. Neither do the scientists who spent their careers preparing the instruments that will read the tubes. None of us know. That is the cruelty and the beauty of science. It gives you an honest answer, but only after you have done the work, and sometimes the answer is not the one you wanted. What we do know now is this. We are closer to the answer than any generation before us has ever been. The 33 tubes are real. The missions to retrieve them are real. The laboratories that will analyse them are real. And the argument that makes the outcome matter, Bostrom's quiet, patient, terrible argument about the great filter is not going away. It has been around for nearly 30 years, and every year more astrobiologists and philosophers and physicists come to take it seriously, not because it is fashionable, but because its logic, once you see it, is hard to unsee. So the next time you hear a headline about Mars, about organics in a rover sample, about a new biosignature, about a fresh announcement from Tianwen-3 or some successor mission, do not just read it as science news. Read it as a weather report from the future. A few more clouds here, a clearing over there, a shift in the forecast about how much time we have and how rare we are, and whether the road ahead of us is long and open or short and narrow. Somewhere on the floor of Jezero Crater, a single titanium tube sits in the dark, saying nothing. And inside it, already, is an answer. We just have not opened it yet. But we will. And when we do, whatever the cosmos has been quietly holding for us will finally come into the light. Our future may turn, in a way almost no one expects, on a tube the size of a cigar sitting under a pink sky, on a cold plain, on a silent world. The universe has already written its sentence. We are simply the ones who have not yet read it. And the only thing left now is to find out which side of the door we have been standing in front of the whole time.